Hello everyone, we will discuss today that every real symmetric matrix is always diagonalizable. Means for any symmetric matrix if we have, then we can write as a diagonal matrix which is similar to that matrix. So we will show it by showing that it has n linearly independent eigenvectors. Means for any matrix A, for any matrix A, if you want to show is diagonalizable, we need to show we have n linearly independent eigenvectors for A. So we know that every non-zero matrix has an eigenvalue. Means for any non-zero matrix A, there exists a eigenvalue lambda and the corresponding eigenvectors v1. So let it eigenvector is v1 and the eigenvalue is lambda. For the non-zero matrix A, we have given A is symmetric matrix. Okay, we know what is the symmetric matrix. A transpose is equal to A. Okay, so now construct a subspace W of Rn such that W is orthogonal to V. What is V? V is a subspan by V1, and we have constructed a subspace which is orthogonal to V. Means that every element of V is and every element of W has dot product as a 0. Okay, so Rn is equal to V and direct sum of W. If you want to prove this, I will prove in another lecture. So by the existence of orthogonal subspace, for any subspace of finite dimensional, we have theorem that for any subspace we have orthogonal subspace such that their direct product is Rn. Obviously Rn is a n-dimensional vector space. Now we try to find out the dot product of v1, which is eigenvector corresponding to lambda. Okay, and the vector A of W, where W is an element of this vector space W. Okay, so by the definition of dot product, it will be v1 transpose A of W. So V is equal to v1 transpose A of transpose W. Because A is symmetric, so we can write A equal to A transpose. Okay, so now we can write this term is equal to A v1 transpose W, but A v1 transpose we have A v1 is equal to lambda v1, because lambda v1 is the eigenvector of A and their corresponding lambda is an eigenvalues. So we have lambda v1 transpose W, as v1 is orthogonal to W, so their dot product will be 0, so the resultant will be 0. So we have seen that v1 dot A of W is equal to 0, means that these vectors are orthogonal, means A of W is an element of W. Okay, so for any W, if we take A of W, we will again get an element in subspace W. So now we can define a linear transformation T bar which goes from T bar such that it goes from W to W. So, and it is defined by induced linear transformation by A. So T of W is equal to A of W. As this is an element of W, we can easily see that it is a linear transformation. So we can show that it is a linear transformation by showing that it is a function first, and T bar is induced linear operator as we have discussed, and by cross T corresponding to A. Again, by existence of eigenvector for non-zero linear transformation. As we know, for any non-zero linear transformation, there exists an eigenvalue. Okay, so for T bar is linear transformation, we should have a eigenvalue. So if 0, then 0 should have linearly independent vectors spanning Rn. Okay, so W is non-zero, because if W is 0, we will get a zero linear transformation. Okay, so for zero linear transformation, there may not be an eigenvalue. Okay, so let mu be an eigenvalue of T bar corresponding to eigenvector V2. Okay, so now we have assumed that this is another eigenvalue corresponding to T bar, and their corresponding eigenvector is V2. So now this V2 is an eigenvector of T bar. So clearly the V2 is a member of W. So since V1 is orthogonal to W, so V1 will be orthogonal to V2 because V2 is element of W. So we can have a span of V1 V2 and direct sum of W equal to Rn by previous theorem. For any subspace, we have assumed this is a subspace because it is a spanning set, and there will exist another subspace such that their direct sum will be Rn by the existence and direct sum theorem. So by similar manner, till when W will be non-zero, we will getting vectors in the spanning set, and all those vectors will be linearly independent because they are orthogonal. So orthogonal vectors are linearly independent. Okay, so when W will be 0, then it will be a span of V1 V2 dot Vk is equal to Rn. It will be till Vn. So we will getting or linearly independent vectors having a spanning set equal to Rn, and all these vectors are eigenvector. Hence we have shown that A is diagonalizable.